Hello friends, to yet another video on TIFR 2020. So in this video we are going to give a solution for a problem that is from linear algebra. This also basically has something to do with diagonalizability of matrices. So let us go to the problem. So the problem is like if A is actually a matrix, an n by n matrix, and we're given a block matrix over here. You can see uh, the question is that if this block matrix is diagonalizable if and only if A is actually a zero matrix, or if A is an identity matrix, or n is equal to 2, or in fact none of the other three options are correct. So we all know that if a matrix is said to be diagonalizable if it is similar to a diagonal matrix D, that is and that diagonal matrix should have nothing but what the entries of the diagonal matrix are nothing but the eigenvalues of the matrix B. So if you're able to do such a thing, then we say that the matrix is diagonalizable. So there are many other characterizations for this. Now or simply if you want to see, we should have something like there should exist a non-singular matrix P such that P inverse BP should be equal to D. Then we can say that B is diagonalizable and D is a corresponding diagonalized form of B. Okay, when you do this diagonalization, usually this matrix P is constructed using the linearly independent eigenvectors of B. So if you have an here we have taken B as an matrix of order n. So if P is obviously has to be of order n. Now if B is having n linearly independent eigenvectors, that means if you find out the eigenvalues of B and if you get exactly n linearly independent eigenvectors, then we can say that matrix is diagonalizable. So it is yet another characterization, but all are the same. So if you're not able to find out n linearly independent vectors of this kind, then we can say the matrix is not diagonalizable. We cannot diagonalize the matrix. Yeah, but yet another interesting characterization for diagonalization of matrices is that or is in fact a necessary and sufficient condition. It is nothing but that the minimal polynomial of that particular matrix should be a product of distinct linear factors. So in the previous video also we have talked about minimal polynomials. We can refer that. So the minimal polynomial has is nothing but it is actually an least degree annihilating monic polynomial which divides every other annihilating polynomials of that matrix B. Such kind of polynomials we call as the minimal polynomial. So for example, if you take B as this matrix, then you can see the minimal polynomial will be x minus 2 whole square, because if you substitute x as B, then we get B minus 2i whole square, which is in fact 0. We can also notice that B minus 2i is not equal to 0. So we can say x minus 2 is not a minimal polynomial, and so on. Now in this problem we are asked to find whether this B is diagonalizable, and if it is diagonalizable, if and only if we need to argue whether if A is 0 or if A is I, or it happens only when n is equal to 2, or like none of these cases. So let us assume this matrix given in this problem to be B. The block matrix is given to us, that we are going to assume it as the matrix B. So if A is equal to 0, that is if you take A to be a 0 matrix and you take the order to be 2 or 3 or 10, whatever bit, but in all those cases the B matrix, that is our block matrix, is diagonalizable, because if we put A equal to 0 we get completely a 0 matrix, and for that particular 0 matrix the characteristic polynomial is going to be x power 2n, and the minimal polynomial is going to be obviously x. So we have the minimal polynomial is x or x minus 0, or we have something like the minimal polynomial is actually a product of linear factors. So we can say that matrix is diagonalizable. So if A is 0, then this B is diagonalizable. Yeah, so clearly what we can see is that option C is false. Now if A is I, that is identity matrix with n is equal to 2 or 3, then the characteristic polynomial of A is going to be x minus 1 power n, and the minimal polynomial of A is going to be x minus 1 because A minus I is actually a 0 matrix. Also, the characteristic polynomial of B is going to be x minus 1 power 2n, but the minimal polynomial of B is not x minus 1 because B minus I will not give you a 0 matrix. So that means that if A is I, our matrix B is not diagonalizable. So we can conclude that option B is not true. Obviously, we have also shown that option C is not true because the sufficient part is not working out there. Because when we took A equal to 0 matrix with whatever be the order, we are getting it as diagonalizable. Yeah. Okay. So now in this case we can see that B minus I is not a 0 matrix, but B minus I power some t will be a 0 matrix. So in that case x minus 1 power t is a minimal polynomial and B is not diagonalizable. So here the minimal polynomial is not a product of distinct linear factors. So option B is false. Yeah. So now what we left out is actually if we finalize the necessary part of the statement for option A, we can confirm whether A or D is correct. Because as far as what we have done is, we could show that if A is 0, we have shown that this matrix is diagonalizable. And if A is I, we have shown it is not, this matrix is not diagonalizable, and n equal to case we have taken out. So if you can show that this matrix is diagonalizable only if A is 0, that is, you can show it is necessary, then we can take out the option D, because then we can say D is not correct. So the interesting part about this kind of matrix B is that if you just simply find B power k and subtract from 2B, and suppose it is equal to 0, then what we can say is that x power k minus 2x is the minimal polynomial of this matrix B. But when you find B power k minus 2b, what you can see is that here this term becomes a power k minus 2a. The same is repeated down here, a power k minus 2a. Here we are getting something like k a power k minus 2a. So whatever be the minimal polynomial of B, suppose we assume it to be say P of B, then P of A is also going to be 0, because P of B is 0. That means if you substitute B in this polynomial P of x power k minus 2x, we are getting it to be 0. So this matrix is a 0 matrix. So a power k minus 2a is also a 0. That means P of the same A, that when you replace x by a, you get P of A, is also 0. So what we can say is that the minimal polynomial of A will divide the minimal polynomial of B. And since we know that here we are given the option that this matrix is diagonalizable, what we can say is that the minimal polynomial of B will be a product of distinct linear factors. And therefore what we have is like this P, the minimal polynomial of this A, which divides this minimal polynomial of B, will also be actually a product of linear factors, because this is actually a product of linear factors. The minimal polynomial of B is linear factors, and this polynomial divides that polynomial. So what we can say is that A is also, since A also has a minimal polynomial which is actually a product of distinct linear factors, we can say that A is also diagonalizable. So the implication what we get here is that if this matrix is diagonalizable, if the B matrix is diagonalizable, then we are getting A is also diagonalizable. But our option, our answer is not that. Like our option is not that. We have to show whether A is 0 or not. So that is what we have to prove here. So now we want to show that A should be, like, we already got that A is a diagonalizable matrix, and if we want this B matrix to be diagonalizable, I think the A must be 0. How we can argue that is, there is a result regarding complex matrices, or in fact it is true for a real matrix also, that if you take a matrix P, n by n matrix P, then it can be written as sum of two matrices Q and N, where Q is a diagonalizable matrix and N is actually a nilpotent matrix. So nilpotent matrix is nothing but a matrix whose power is zero matrix for some k greater than some k, some real number k, and for all integers say from 1 to k minus 1, it is not zero. So such kind of matrices we call as nilpotent matrices, and these matrices Q and N will commute. So for every complex matrix we can go for we will get such matrices Q and N for which Q is diagonalizable and N is nilpotent matrix, and this Q and N will commute. So here if you just see this matrix, we can write our matrix as sum of these two matrices. One is a diagonal matrix, another is actually a matrix of this form. In fact, this is actually an nilpotent matrix. You can try, you can go on squaring this matrix, it will become 0 after some time. So here we have the fact that A is a diagonalizable matrix. So this matrix, this diagonal matrix is actually a diagonalizable matrix because it has two blocks, and the block matrices, if they are diagonalizable, then we can say this matrix is this diagonal matrices, diagonal blocks, when they are diagonalizable, then we can say this matrix is diagonalizable. So this portion is diagonalizable matrix. This is our Q here, and if you choose N to be this 0, A 0, 0, then this is actually the nilpotent part. So what we can say here, we can also see that if you just multiply Q with N and with N with Q and you compare, they are same. That means Q and N will commute. So from here we can say that if you want this matrix to be a diagonalizable matrix, the nilpotent part of the matrix has to be 0. That means this A has to be 0. So thus we get that A has to be 0, and then we can conclude that option A is correct and option D is false. So thank you for watching this video. So please subscribe my channel for further problems and updates. Thank you.